Greetings, Mr. Sutton here, bringing you the AB Calculus 3-3 Extra Practice Number 2 solutions on differentiability, Part 2. On this problem, we want to know if this piecewise function is differentiable at the border value x equals 2. So to test that, we have to first check to see if it's continuous, and then we'll check to see if the limits of the slopes match up. So checking continuity, we first look at the limit as x approaches 2, and for that we have the left and the right side limit. Left side limit at 2, we're going to be using this less than 2 rule. So we've got negative 2 squared plus 3 times 2. So that's negative 4 plus 6, which ends up being positive 2. Now for the right side limit at 2, we're using this greater than 2 rule. So 3 times 2 squared, which is 3 times 4, which is 12, minus 10 comes out to 2. And then finally, we also have to talk about f of 2, the function value, or else we're not talking continuity, we're just talking limits. So f of 2 is just going to match up with the left side limit here because it happens to share the same rule if x equals 2. So that is again going to be the value 2. We see here that the limit as x approaches 2 and f of 2 match up and both exist. Therefore, our function is continuous at x equals 2, but is it differentiable? To check on that, now we have to actually look at f prime, specifically the limit of f prime as we approach 2 from both sides. So let's check first the left side limit of f prime at x equals 2. For that, we have to use the before 2 rule and take the derivative of this first rule. That's negative 2x plus 3. So now the limit as we approach 2 for this function, that's going to be negative 2 times 2, which is negative 4, plus 3 gives us negative 1. Now we need the right side limit as we approach 2 for f prime. That's using this second rule. Using the power rule on this, we have 6x, limit as x approaches 2 from the right. And then that's going to be 6 times 2, which gives us 12. So we see here that the left and the right side limits of f prime are not the same. The slopes don't match up. Therefore, our function is not differentiable at x equals 2. For this one, we're trying to see if this piecewise function is differentiable at the border value 0. Let's start by finding the limits and function values at 0. So we have to start with the left side limit as we approach 0. That's going to use this less than 0 rule right here. Plugging 0 into this just zeroes everything out because everything has a variable. So that just comes out to 0. The right side limit at 0, now we're using the greater than 0 rule here. That also comes out to 0 if we plug that in. And then the function value, f of 0, that's just the same as this right side limit, happens to use the same rule, also 0. So we see here that the limit as x approaches 0 and f of 0 are the same. So the limit exists, the function exists, and they equal each other. So this function is continuous at x equals 0. Is it differentiable? We have to look now at f prime as we approach 0 from the left and the right. So the left side limit of 0, of f prime at 0, I should say. That's going to be taking the derivative of this before 0 rule. So we're basically plugging 0 into 2x plus 5. And plugging 0 into this, we're just going to end up with the constant 5. Next, I need the right side limit of f prime at 0. So now we're using this after 0 rule, which is going to be, if you take the derivative, 4x minus 3. Plugging 0 into that is going to give us just negative 3. We see that the left and right side limits of f prime do not match up. Therefore, our function is not differentiable at x equals 0. For this one, we want to see if our function is differentiable at the border value x equals 2. Let's start by checking the limit and the function value for continuity. So left side limit at 2, that's going to be using this less than 2 rule. So plugging 2 in here, we have 2 times 2 squared, so 2 times 4, which is 8. Minus 2 gives us 6. Now checking the right side limit at 2, we're using this after 2 rule. So 8 times 2, which is 16, minus 22 gives us negative 6. And we see right away before we do anything else, the left and the right limits do not agree, so the overall limit as x approaches 2 does not exist. Therefore, the function is not continuous at x equals 2. Therefore, because continuity is a requirement for differentiability, the function is also not differentiable at x equals 2. And that should say positive 2. There we go, positive 2. On this one, we want to know if our function is differentiable at the border value 4. So let's start by testing for continuity, and then we'll go from there. So I need to check the left and right side limits and also the function value. Left side limit at 4 is going to be, using this first rule here, the less than 4 rule. So 2 times 4 plus 3, that's 8 plus 3, or 11. Next, for the right side limit at 4, we're using the after 4 rule. So that's going to be 4 squared, so 16, minus 5 gives us 11 as well. And then the function value, which we have to mention, f4, that's going to just use this first rule again, so that again gives us 11. All right, so we see here that the limit as x approaches 4 and f of 4 both exist and equal each other. Therefore, our function is continuous at x equals 4. So we can go ahead and check to see if the slopes match up at x equals 4. So now we're going to take the left and the right side limit of f prime as we approach 4. So left side limit of f prime at 4, we're going to be taking the derivative of this before 4 rule, so the derivative of 2x plus 3. That's going to just end up being a constant value of 2, so that is the left side limit of f prime. Now for the right side limit of f prime at x equals 4, we're taking the derivative of the after 4 rule. That's going to be 2x. The 5 is just a constant, so that becomes 0. So we're doing limit as x approaches 4 from the right of 2x, which is basically just 2 times 4, or 8. The left and the right side limits, unfortunately, do not match up, for f prime at least. So that means that our function's slopes don't match up. We probably have a corner. We are not differentiable. On this problem, we're asked to determine if this piecewise function is differentiable at 1, and if it is, to find the value of the derivative at x equals 1. Okay, well, let's go ahead then and check for continuity first. So left side limit as x approaches 1, that's going to be using my less than 1 rule, so plugging 1 into x squared plus 1. So that's really 1 squared plus 1, which comes out to 2. Next, the right side limit at 2, we're using the after 1 rule here. 2 times 1 also gives us 2. And then f of 1, which we have to mention for continuity's sake, that's going to just be using our first rule again because of the equals here, so that again is a value of 2. Well, we've demonstrated that the limit exists, that the function value exists, and that the limit and the function value are the same at x equals 1. Therefore, our function is continuous at x equals 1, which is a good start. It's not enough, but it is necessary. Now we're going to see if the limits of f prime as we approach 1 match up. So left side limit as we approach 1 from the left of f prime, we're going to be using the derivative of my first rule, my before 1 rule here. So that's the limit as x approaches 1 of 2x, which is just 2 times 1, or 2. Next, we're going to check out the right side limit of f prime. So that's using the derivative of this second rule, the after 1 rule, which is just going to be a constant value of 2. Well, these match up, so therefore, because my slopes match up, this function is going to be differentiable at x equals 1. That means we can actually take the derivative at x equals 1. So f prime of 1 is just going to use whichever rule had the 1 inside of it here. It actually should come out the same regardless of which rule you use, because you just checked to make sure that the slopes actually matched up. So in both cases, both slopes gave us 2. This should come out to f prime of 1 equals 2. For this one, we have this weird piecewise function with an a and a b that they're not telling us what they are. They want us to actually find those and find an a and b that make this function differentiable. Well, if we take a look at the individual rules, this function is continuous on both of these rules. They're both polynomials. Therefore, and it's also, you can also take the derivative of a polynomial for sure. So we are definitely differentiable within each rule. All the x values are defined for this function. So really the only place where we could mess up differentiability is going to be at the border value. So that means we have to, in order to find a and b, we basically have to prove that this thing is continuous and differentiable at that border value. And the equations that we create in proving that are going to give us something we can use to solve for a and b along the way. All right, so let's test for continuity first. So I have to take the left and the right side limit at 2. So left side limit as x approaches 2. That's using the before 2 rule. Plugging 2 into this, we're going to have 2 cubed, which is 8. So 8a plus 1. and then the right side limit at 2. Now we're using the after 2 rule. So this is going to be b times 2 squared, so b times 4, or 4b plus 9. And we can't really do anything with a and b at this point because we don't know what they are, so we're just going to kind of leave them around. And because we want to show that these are a and b values that make this function differentiable, that means we also have to show f of 2, the function value. Otherwise, whatever value of a and b we get, we're not guaranteed that it also makes this continuous. So that the good news is that f of 2 just uses this second rule, just like the right side limit. So I'm just going to kind of piggyback f of 2 after this right side limit that we took. So we're indicating to people that f of 2 and the right side limit both are 4b plus 9. All right, in order for this function to be continuous, the limit has to exist and equal the function value. That means that 8a plus 1 and 4b plus 9 have to be the same value, have to equal each other. And this is going to give us an equation that we can use to help us solve for a and b. Unfortunately, we can't solve just using this equation. We're going to need more information, but it's a good start. So we're going to get the other equation by taking a look at the limit of f prime as x approaches 2 from the left and the right. So this is basically the second half of our differentiability test. So now the left side limit as x approaches 2 of f prime, we're going to be taking the derivative of the before 2 rule here. So derivative of ax cubed plus 1, that's going to be 3ax squared that we're plugging 2 into. And that's going to be, let's see, 3 times a times 4, so that's 12a. Now we have to take a look at f prime as we approach 2 from the right side, so another limit here. And that's going to be using this second rule. So derivative of the second rule, that's going to be 2bx, and the 9 is gone. So we're plugging 2 into 2bx, the derivative of bx squared plus 9. This is going to be 2 times b times 2, so that's 4b. In order to be differentiable, this function needs to have these f primes match up. So that means 12a and 4b must also equal each other. All right, so we have two equations. We can solve this system of equations now. Just to be a little bit cheap and take a shortcut here, you'll notice that 12a and 4b are the same value. They equal each other. Well, hey, here's a 4b in this other equation. That means that this 4b must also equal 12a. So I can replace this whole 4b here with 12a. Pretty sweet, huh? I mean, I could have gotten b by itself and then done a substitution that way. We could have used elimination by subtracting this equation from this equation. There's a lot of different ways to do these. I just chose this method. Use whichever way works for you. But now solving for a, we can subtract 8 over here to give us 4a and subtract the 9 over here to give us negative 8. So we have, or we can go the other way, negative 4a and positive 8. Either way, half a dozen of one, 6 of the other. So we then end up with a equaling negative 2. Now we can go back and plug negative 2 in to one of these equations to figure out the b value. I'm going to plug it into this second one here. This one looks pretty easy. So we've got 12 times negative 2 equals 4b. This is negative 24 equals 4b. So therefore b has to equal negative 6.